Hi, this is video 1.3a, introducing evaluating limits algebraically as opposed to graphically in section 1.2 where you were given a graph. So, analytically means the same as algebraically, and the first strategy you will always use when trying to evaluate a limit algebraically is simple substitution. If indeed you get an answer that exists, a real number, you are done. However, there are many cases where instead of getting an actual real number, you will get some kind of a does not exist situation due to, for example, 0 over 0. So we're just going to concentrate on that for now. What happens if substitution yields 0 over 0? There are three options. You can try any one of these. I'm not saying you're doing all of these. It'll depend on the situation. If you can factor the numerator and denominator, of course we have a numerator and denominator, then do so and cancel. If there are radicals involved, then maybe you'll be rationalizing the numerator or the denominator. I know you're used to rationalizing only denominators in Algebra 2 and Pre-Calc, but if the radicals are in the numerator and not in the denominator, you'll rationalize the numerator. Third case scenario, if you get 0 over 0, is to try and simplify the expression. Maybe it's a complex fraction and you can simplify it. So here's an example. What it does, all it says is find the limit if it exists, and here's an example right here. So remember, the first thing we always try is substitution. If I do try substitution, if I replace x by 0, I will get root 2 minus root 2 is 0, and if I substitute in x equals 0 on the denominator, I'll get 0 over 0. You're not going to factor this, you're not going to simplify this, but you can rationalize the numerator. So remember, you're dealing with a situation where you have an irrational numerator and you want to rationalize it. You want to get rid of the two radicals. The way to do that is to multiply by what we call the complex conjugate, which means if you have a minus b, you'll need to multiply by a plus b. Now don't forget that you are doing this both to the numerator and the denominator. Many students will forget that that's there in the denominator. So what happens on the top, of course, when we multiply a minus b times a plus b, we get a squared minus b squared, which will be the square of this radical, which will give just 2 plus x, and then minus, and then the square of the second term, which will just be 2. Now the beauty of that, of course, is the fact that 2 plus x minus 2, the 2's will cancel, leaving you with x. Now again, don't forget, you don't just have x in the denominator, you also have root 2 plus x plus root 2. So leave this in factored form. I cannot emphasize with enough happy faces that you need to leave this in factored form. Reason being, when these 2's cancel, because it's in factored form, you'll be able to cancel the x's. You'll now be left with this expression in the denominator. You now replace x by 0 in the denominator. The numerator is just 1, and you will get your final answer of 1 over 2 root 2 because you get root 2 plus root 2. I do want to remind you that in AP Calculus, there is no need to rationalize the denominator of a final numerical answer. So again, notation-wise, and we talked about this before, notice how in every line since the beginning, I keep writing the limit as x approaches 0, limit as x approaches 0, all the way down to this step. Now the reason I write it all in these other steps is I have x's still. But once I do the substitution and I no longer have x's, the limit has to disappear. The answer is just 1 over 2 root 2. All right, it will be important in this course that you know how to factor the sum and difference of two cubes, something you learned in Algebra 2 for probably one day, and something that came up in pre-calc for maybe 1 or 2 days, but this will come up quite often for us. So here is the factorization of the sum of two cubes. Here's the factorization of the difference of two cubes. Make sure you are keenly aware of this and that you understand how this works. This is the cube of x, which is why this is x squared, and x. This is the cube of 2, which is why that's 2, 2, and 2 squared. So if you need to take a little time to look at this page, please pause. And there is a way of sort of cheating in these situations if you substitute and get 0 over 0. So for example here, if I replace x by 3, I get 0. 3 squared is 9 times 4 is 36. 3 times 7 is 21. 36 minus 21 happens to be 15, and 15 minus 15 is 0. So if you establish that you have 0 over 0, then keep in mind that the reason the numerator is 0, of course, is because the numerator has a factor of x minus 3. Well, obviously, if the denominator is 0, that means that this denominator must have a factor of x minus 3 as well. So if you write the x minus 3 down, it makes it easy to factor this. You know this is x. X times what gives 4x squared? You know that's 3. 3 times what gives 15. The x minus 3's cancel. Notice the limit is still there because there's still x's. And then you substitute and, of course, get an answer of 1 over 17. Some basic limits. Obviously, the limit as x approaches 3, for example, of 7 is still going to be 7 because what you have, if you think about it, is a line. Do this. For this one, it would be like you have a line y equals 6. Well, obviously, the limit as x approaches any number, including 2 or 5 or whatever, of my function y would equal 6. Okay, because the height is always 6. Sorry, that's an x. Okay, limit as x approaches c of x. Well, if you have y equals x, obviously if you substitute and you replace x by c, you'll get c. Same thing in the third one. If you replace the x by c, you'll get c to the n. Now, the difference here is that there is no x to replace by it, but keep in mind you are dealing with a linear horizontal line. Properties of limits, they look complicated. All that this is telling you is that if you have a constant times a function and you're finding the limit of that, you can pull that constant on the outside. For example, this is right what I'm talking about. If you have the limit of the sum or difference of two functions, you can split that up into the sum or difference of the limits of each of the functions. Same thing with product can be split up. Same thing with quotient can be split up as long as the denominator is not 0. And exponents can be pulled on the outside or back on the inside, no problem. So these are just very basic properties. Again, you can go back to that page and look at them. They say use the information to evaluate the limits, and we're going to be using the properties that we just saw. So they give you two limits. Now, you can't do these algebraically because you don't know what f of x and g of x are, so you have to use the properties. Here, you're going to pull out the 4. Here, you're going to split it up into the limit as x approaches c of f of x plus the limit as x approaches c of g of x. Here, you'll split up the product, and here, you'll split up the quotient. So as you can see, for the first one, I pull out the 4. I'm left with 4 times the limit as x approaches c of f of x, which they told us is 3/2. Next one, I'm going to break it up into a product of limits, and they gave us each of those, etc. And that's the end of video 1.3a.